What you're about to hear is the story of one of the biggest scientific mistakes in the history of space exploration, and almost nobody knew about it for nearly 40 years. It happened in complete silence, 45,000 miles above a tilted, freezing blue planet, and it changed the way every textbook on Earth described that world. Nobody planned it. Nobody could have stopped it. And the strangest part is that the mistake was not caused by a broken camera, a computer glitch, or a human error back on Earth. It was caused by the sun itself, at the exact wrong moment, on the exact wrong day, in a window of time so small that scientists now say it only happens 4% of the time. If the spacecraft had arrived even a few days earlier, everything we think we know about this planet would be different. Let that sink in for a second. For almost 40 years, students memorized facts about this planet that may never have been true in the first place. Scientists built entire theories on top of information gathered during what researchers are now calling a freak accident of timing. And it all traces back to a single flyby, a single spacecraft, and a single planet that nobody has visited since. That planet is Uranus, the seventh planet from the Sun, and the only close-up look humanity has ever gotten of it came from a spacecraft called Voyager 2 back in January of 1986. Voyager 2 did not stop, did not orbit, did not linger. It flew past Uranus once, took its readings during a window of about 5 hours, and then kept going, deeper into the solar system, never to return. Think about that for a moment. Everything scientists have taught the public about Uranus for the last several decades, its magnetic field, its radiation belts, its moons, all of it came from a single 5-hour pass by a robot that was already on its way somewhere else. There was no second attempt, no follow-up mission, no way to double-check the data. Whatever Voyager 2 saw in those few hours became the permanent record, the foundation, the accepted truth. And that is exactly why what scientists discovered recently is so shocking. It turns out that single flyby might have caught the planet at the worst possible moment, a moment so unusual, so rare, that it may have completely distorted everything we thought we understood. Let's go back to that day in January 1986 and understand what actually happened, because the story only gets stranger from here. Uranus is already one of the strangest planets in our solar system. Unlike every other planet, which spins more or less upright as it orbits the sun, Uranus is tipped over on its side. It rotates almost completely sideways, like a ball rolling instead of a top spinning. Nobody fully agrees on why this happened, though many scientists believe an ancient, massive collision knocked the planet onto its side billions of years ago. So even before Voyager 2 arrived, this was already a bizarre, off-kilter world unlike anything else nearby. When the spacecraft finally got close enough to take detailed readings, what it found made Uranus seem even stranger. The planet's magnetic field was not aligned with its rotation the way Earth's magnetic field roughly lines up with its spin axis. Instead, Uranus's magnetic field was tilted at a steep, lopsided angle, offset from the center of the planet in a way that made almost no sense compared to other worlds. On top of that, the spacecraft detected radiation belts around the planet that were surprisingly intense, second only to the crushing radiation belts found around Jupiter, the largest planet in the solar system. And yet, despite all that intense radiation, the region of space around Uranus appeared to be almost completely empty of plasma, the electrically charged particles that usually fill the space around magnetized planets. This combination confused scientists for decades. High radiation, but almost no plasma. A wildly tilted off-center magnetic field. It did not look like anything else Voyager had encountered at Jupiter, Saturn, or Neptune. And so scientists did what scientists do. They built an explanation around the data they had. They concluded that Uranus was simply different, a naturally weird outlier in the solar system, with a magnetosphere and moon system that behaved unlike any other planets. Because the plasma readings were so low, researchers also concluded that the large moons orbiting Uranus, worlds with names like Titania, Oberon, Ariel, and Umbriel, were essentially dead, geologically inactive, frozen, silent, unchanging chunks of ice and rock with nothing happening beneath their surfaces. That conclusion shaped scientific priorities for Uranus and its moon system for the next several decades. If the moons were dead, they were considered less interesting targets for future exploration. Funding, mission proposals, and scientific attention drifted elsewhere, toward moons like Europa and Enceladus, which showed much more obvious signs of activity. In other words, an assumption made from a single 5-hour flyby may have quietly shaped where humanity chose to look, and where it chose not to look, for the next 40 years. Now here is where the story takes its twist. Decades later, a team of researchers, led by a space plasma physicist named Jamie Jasinski at NASA's Jet Propulsion Laboratory, decided to go back and take a fresh, modern look at the old Voyager 2 data. Not new data. Not a new mission. The exact same numbers that had been sitting in NASA's archives since 1986, just waiting for someone to look at them with new eyes and new tools. And what they found completely upended the story that scientists had believed for almost 40 years. According to their analysis, just days before Voyager 2 made its flyby, Uranus had been hit by an unusually powerful burst of solar wind, a stream of charged particles blasting outward from the sun. This was not an ordinary, everyday gust of solar wind. It was an extreme spike, a rare event that dramatically compressed and squashed the planet's magnetosphere, the protective magnetic bubble that surrounds Uranus and shields it from space radiation. Imagine a balloon getting suddenly squeezed from the outside, shrinking down and losing its normal shape. That is roughly what happened to the space around Uranus in the days leading up to Voyager's arrival. The intense solar wind compressed the magnetosphere, and in doing so, it appears to have swept away much of the plasma that would normally have been present. That explains the almost empty plasma readings Voyager 2 recorded, not because Uranus is naturally some strange plasma-free anomaly, but because the spacecraft arrived in the immediate aftermath of a violent solar event that had just blasted the area clean. According to the research team, this kind of extreme compression event only happens around 4% of the time. In other words, on any random day you might choose to fly past Uranus, there is roughly a 96% chance you would see completely different conditions than what Voyager 2 actually recorded. Jasinski summed up the strange coincidence by explaining that if Voyager 2 had simply arrived a few days earlier, before the solar wind event hit, it would have observed a completely different magnetosphere at Uranus altogether, a few days. That is the entire margin between the version of Uranus we have believed in for nearly 40 years, and a completely different planet that we never got to see. Voyager 2 essentially caught Uranus on its single worst possible day, a snapshot taken during an extreme and temporary disturbance, and scientists mistook that temporary disturbance for the planet's normal, permanent state. It would be like a doctor examining a patient in the middle of a sudden fever and using those results to define what a normal, healthy version of that person looks like for the next 40 years, never realizing the fever was temporary at all. This new interpretation does not just tidy up an old scientific mystery. It has the potential to rewrite fundamental assumptions about the entire Uranian system. Remember that conclusion about the moons being geologically dead based on the apparent absence of plasma. If the missing plasma was simply a temporary side effect of an unusual solar storm rather than a permanent feature of the environment around Uranus, then the reasoning behind labeling those moons as inactive falls apart. Scientists are now reconsidering whether some of Uranus's largest moons might actually be far more active than previously believed, potentially featuring subsurface oceans, geological activity, or other dynamic processes that were simply never detected because Voyager 2 happened to fly through during an atypical, disturbed environment. This is not just a minor correction. This is the kind of discovery that can quietly redirect the entire future of planetary exploration, deciding which distant moons scientists prioritize studying and which ones get overlooked for decades. It is worth pausing here to really appreciate how strange this situation is from a scientific perspective. Usually, when we talk about a groundbreaking discovery, we imagine new data streaming in from a brand new mission, a spacecraft arriving somewhere for the very first time, cameras clicking, instruments buzzing with fresh information. This story is different. Nothing new was collected. No new spacecraft was launched. The breakthrough came entirely from scientists returning to decades-old numbers, sitting quietly in an archive, applying new analytical methods and a modern understanding of space weather, and realizing that the story everyone had accepted for a generation may have been built on a fluke. It is a powerful reminder that the story science tells us about the universe is not necessarily the final story. It is simply the best available interpretation of the data collected at that particular moment, which can be limited, incomplete, or in this case, badly timed. There is something almost eerie about imagining that flyby happening in real time. Voyager 2, a spacecraft roughly the size of a small car, hurtling through the freezing darkness of the outer solar system, arrives at a planet that has just been struck by an invisible storm from the sun, 93 million miles away. Nobody planned it that way. Nobody on the mission team back on Earth had any way of knowing, in the moment, that the numbers streaming back across billions of miles of space represented anything unusual. As far as anyone could tell at the time, this was simply what Uranus looked like. The data was recorded, transmitted home, and locked into the scientific record as fact. And it stayed that way, unquestioned in its core interpretation, for the better part of 4 decades, until a small team decided to dig back into it with fresh eyes. This story also highlights just how limited humanity's direct knowledge of Uranus really is. Every image, every reading, every fact we think we know about this ice giant traces back to that single flyby. No orbiter has ever circled it. No lander has ever touched its clouds or its moons. No follow-up probe has ever gone back to verify or expand on what Voyager 2 saw. For nearly 40 years, an entire planet, one of only 2 ice giants in our solar system along with Neptune, has essentially been studied through a single, brief drive-by encounter. Compare that to planets like Mars or Jupiter, which have been visited by multiple missions orbited for years at a time, and studied through repeated observations that allow scientists to build a much clearer, verified picture. Uranus has had none of that. Everything rests on one dataset collected during a matter of hours, and now, on top of that, we learn those hours may have captured the planet in one of its rarest and least representative states. Naturally, this new understanding has reignited calls from scientists around the world for a dedicated return mission to Uranus. Researchers like Johnny Horner, an astronomer who has spoken publicly about the need for further study, have argued that a future mission should not simply fly past the planet the way Voyager 2 did. Instead, it should be designed to orbit Uranus for an extended period, allowing scientists to observe the planet's magnetosphere, radiation belts, atmosphere, and moons across many different conditions, rather than relying on a single fleeting snapshot that could easily be misleading. This idea is not just wishful thinking from a handful of scientists. It has gained serious institutional backing. The National Academies of Sciences, in a major influential planetary science survey released in 2022, formally identified a mission to Uranus as one of the highest priorities for the coming decade, urging NASA to invest in a spacecraft capable of orbiting the planet for an extended stay, rather than repeating the mistake of a brief flyby. There have even been reports discussing potential timelines for such a mission. According to reporting, referencing a 2023 feature in Scientific American, NASA has discussed plans that could see a spacecraft launched by around 2032, designed specifically to enter orbit around Uranus, and even send a probe plunging down into its thick, freezing atmosphere. If a mission like that actually moves forward, it would represent the first time in human history that any spacecraft has ever orbited Uranus, rather than simply passing by. It would allow scientists to finally answer the questions that have lingered since 1986. Is the magnetic field really as strangely tilted and offset as it appeared? Are the radiation belts really as intense as recorded? And most intriguingly, are those large icy moons truly geologically dead? Or are they secretly hiding oceans and activity beneath their frozen surfaces? The kind of environments that scientists increasingly believe could be capable of supporting the ingredients for life. Voyager 2's project scientist, Linda Spilker, who has been involved with the mission for decades, has said that this new analysis is likely to change our view of Uranus once again. That phrase is worth sitting with for a moment. Change our view of Uranus once again. It implies that our understanding of this planet has always been somewhat fragile, always resting on incomplete information, always subject to revision the moment new analysis or new missions become available. For a planet that so few people think about, so far away, so cold, so quietly overlooked compared to Mars or Saturn, this story is a powerful reminder that there are still fundamental mysteries about our own solar system that remain unsolved, sitting quietly in old data, waiting for someone to notice. There's also something almost poetic about how this mistake happened in the first place. It was not caused by faulty equipment. It was not caused by human error in calculating trajectories or interpreting instruments. It was simply bad timing, the kind of coincidence nobody could have predicted or prevented. Voyager 2 launched years before it ever reached Uranus, following a carefully planned trajectory that took advantage of a rare alignment of the outer planets, allowing it to visit Jupiter, Saturn, Uranus, and Neptune all in a single extended mission. That trajectory could not simply be adjusted at the last minute to avoid a solar storm that nobody could have predicted years in advance. The spacecraft arrived when it arrived, and the Sun, completely indifferent to NASA's mission planning, happened to unleash an unusually powerful burst of solar wind at precisely the wrong moment. It is almost unsettling to think that something as massive and complex as our understanding of an entire planet could hinge on such a small, random accident of timing. For anyone who has ever looked up at the night sky and wondered how much we truly understand about the universe around us, this story offers a humbling answer. Even something as seemingly solid and well-established as the basic physical properties of a planet in our own solar system can turn out to be far less certain than anyone assumed. Uranus is not some distant exoplanet light years away, glimpsed only through faint telescope signals. It is a planet right here in our own solar system, one of only 8 major planets orbiting our sun, and yet even here, close to home in cosmic terms, our knowledge has quietly rested on a foundation that may have been cracked from the very beginning. So what happens now? For the time being, scientists are left revisiting old assumptions, re-examining old data, and pushing harder than ever for a dedicated mission that could finally give humanity a real, extended, reliable look at this strange sideways planet and its potentially active moons. Until that mission happens, if it happens, everything we think we know about Uranus remains, in a very real sense, still shaped by 5 hours in January of 1986, 5 hours that may have captured this ice giant on its single, strangest, most misleading day. The full truth about Uranus, its magnetic field, its radiation belts, and the secret lives of its icy moons may still be waiting out there in the darkness, hidden behind a curtain that a random burst of solar wind accidentally pulled, shut nearly 40 years ago. And until another spacecraft finally makes the long journey back, we are left wondering just how different our picture of this planet might have been if Voyager 2 had simply arrived a few days sooner. Let's slow down for a moment and really think about what it means for a piece of science to sit unquestioned for 40 years. 40 years is not a short amount of time. It is longer than most careers. It is long enough for the scientists who first analyzed that Voyager 2 data to retire, and in some cases, to pass away, never knowing that a future generation would go back and challenge their conclusions. It is long enough for entire textbooks to be written, printed, revised, and reprinted, all repeating the same description of Uranus as a naturally strange, plasma-starved world with dead, frozen moons. It is long enough for museum exhibits to be built around that idea, for documentaries to be filmed explaining it to millions of viewers, for students in classrooms around the world to memorize it for exams without ever questioning where the information actually came from. That is the quiet power of a single data set. Once something becomes the accepted explanation, it tends to get repeated again and again, until almost nobody remembers to ask whether the original data itself might have been flawed from the start. And this is not the first time in the history of science that something like this has happened. Scientific understanding is often built in layers, with each generation adding to, or sometimes correcting, the work of the generation before. Ideas that once seemed absolutely certain have been overturned before, sometimes gently, sometimes dramatically. What makes the Uranus story so striking is not just that a correction happened, but how close the margin was. This was not a case of scientists slowly gathering more evidence over the years and gradually shifting their view. This was a case of one brief encounter, one specific 5-hour window, happening to land during an event so rare that it occurs only a small fraction of the time. If you tried to design an experiment specifically meant to produce a misleading result, you almost could not do better than accidentally timing your only observation to coincide with a freak solar storm. Think about the sheer scale of the coincidence involved here. Voyager 2 launched in 1977. It took 9 years, traveling through the emptiness of space, using the gravity of Jupiter and Saturn to sling itself further outward, before it finally reached the vicinity of Uranus in January of 1986. 9 years of travel, careful trajectory corrections, instrument calibrations, and mission planning, all leading up to a 5-hour encounter with a planet nearly 2 billion miles from Earth. And within that narrow 5-hour window, the spacecraft happened to arrive during a period that researchers now estimate occurs only about 4% of the time. If you tried to schedule a 5-hour appointment at any random point across an entire year and there was only a 4% chance of landing during a specific rare weather event, most people would call that wildly unlucky. Except in this case, it was not just unlucky for one afternoon. It was unlucky for an entire scientific field for nearly 4 decades. It also raises an unsettling question that reaches beyond Uranus itself. If a single flyby of a planet in our own solar system could end up misleading scientists for 40 years, what does that say about our understanding of other worlds we have only glimpsed briefly, or not glimpsed directly at all? Every distant moon, every asteroid, every planet in our solar system that has only been visited once, briefly, by a passing spacecraft, could potentially be hiding a similar surprise. A single flyby of any world only ever captures a narrow slice of time, a snapshot that may or may not represent what that world actually looks like most of the time. For planets and moons we have visited repeatedly, like Mars, that risk is smaller because scientists have multiple observations across different conditions to compare. But for places visited only once, briefly, the risk of building an entire scientific understanding on top of an unrepresentative moment is very real, and Uranus may simply be the clearest, most well-documented example of that risk actually playing out. There's another layer to this story that deserves attention, and it has to do with how science actually corrects itself. It would be easy to look at this discovery and assume that scientists in 1986 simply made a careless mistake, failing to notice something obvious. But that is not really what happened. At the time, researchers analyzed the data they had using the best tools, models, and understanding available in the 1980s. Space weather science, the study of how solar activity affects the space environment around planets, was still a relatively young and developing field. The instruments on Voyager 2, while remarkable for their time, were designed decades before the mission even launched, using technology that seems almost primitive by today's standards. The scientists who first studied that data were not being careless. They were doing careful, rigorous science with the tools and knowledge they had available at the time. It was only decades later, with a far deeper understanding of solar wind behavior, magnetospheric physics, and access to modern computational analysis methods, that researchers were able to look back at those same numbers and notice a pattern that simply was not visible to anyone in 1986. That is worth remembering, because it reframes this story from being about a mistake into being about the natural, ongoing process of scientific discovery. Science does not claim to deliver permanent, unchangeable truth the moment a mission returns its first results. It delivers the best possible interpretation available at that time, based on the tools, knowledge, and context that exist in that moment. And as tools improve, as understanding deepens, as new generations of scientists revisit old questions with fresh eyes, interpretations can and do change. In this case, the underlying numbers recorded by Voyager 2 in 1986 never changed at all. What changed was humanity's ability to correctly interpret what those numbers actually meant. This also says something remarkable about the value of old data. In an age where space agencies are constantly racing toward the next big mission, the next new launch, the next headline-grabbing discovery, it is easy to overlook the immense value hidden inside archives of old, already collected data. NASA did not need to build a new spacecraft, spend billions of dollars, or wait 9 more years for a probe to reach Uranus again in order to make this discovery. All it took was a team of dedicated scientists willing to go back, dig through decades-old readings, and apply modern analytical techniques to information that had been sitting quietly in storage the entire time. In many ways, this discovery is a reminder that the answers to some of our biggest remaining questions might not require new missions at all. Sometimes they're already sitting in an archive somewhere, waiting for someone with the right expertise and the right curiosity to take a second look. Of course, the deeper implications of this discovery go far beyond simply correcting an old scientific record. If the moons of Uranus really are more geologically active than previously believed, the consequences for planetary science, and possibly even the search for life beyond Earth, could be significant. In recent years, scientists have become increasingly interested in what are called ocean worlds, moons throughout the solar system that may harbor liquid water, oceans hidden beneath thick, icy outer shells. Moons like Europa around Jupiter and Enceladus around Saturn have become priority targets for exploration precisely because evidence suggests they may have subsurface oceans, and where there is liquid water, there is at least the possibility of the right conditions for life to exist. For decades, Uranus's large moons were largely left out of that conversation, dismissed as cold, inactive, and geologically unremarkable, based largely on the plasma readings collected during that single 1986 flyby. If that assumption turns out to be wrong, if the missing plasma was simply a temporary side effect of an unusual solar storm rather than a permanent feature of an inactive system, then Uranus's moons may deserve a second look, and possibly a much higher place on the list of worlds worth exploring in search of environments capable of supporting life. It is almost strange to imagine that somewhere out there, right now, one of Uranus's large icy moons might be quietly hiding a liquid ocean beneath its frozen surface, completely unnoticed for nearly 40 years, simply because the only spacecraft ever sent to examine it happened to arrive during a rare, misleading moment of cosmic bad timing. It is the kind of detail that sounds almost too strange to be real, and yet it is exactly the situation scientists now find themselves reconsidering. As this story continues to unfold, one thing is clear. The case for sending a dedicated mission to orbit Uranus has never been stronger. Scientists are no longer simply curious about a distant, sideways spinning oddity at the edge of the solar system. They now have direct evidence that our entire understanding of this planet may be built on a flawed foundation, shaped by an unlucky roll of cosmic timing rather than the planet's true ordinary behavior. An orbiting mission would finally allow researchers to observe Uranus across many different conditions, watching how its magnetosphere behaves not just during one narrow 5-hour window, but across weeks, months, or even years, capturing the planet's true, typical behavior rather than a single, potentially misleading snapshot. Until that mission becomes a reality, the story of Uranus remains a powerful example of how much of what we accept as scientific fact is really our best current interpretation of limited evidence, always open to revision as our tools and understanding improve. It is a story about a planet that briefly, almost accidentally, misled an entire field of science, not through any fault of its own, but simply because of when a small spacecraft happened to pass by. And it is a story that is far from over because somewhere out past Saturn, tilted on its side, wrapped in freezing blue clouds, Uranus is still waiting, quietly holding on to secrets that may finally be revealed the next time a spacecraft from Earth makes the long journey back. So, the next time someone tells you a scientific fact with complete certainty, remember this planet, remember those 5 hours in January of 1986, and remember that even the most solid-seeming knowledge about our own solar system can quietly hinge on nothing more than a few days of unlucky timing, waiting decades for someone to finally notice.